start the recording now. Just 1 minute. Get started. So everyone, we are going to start our second session. That is on estimation of parameters. So and there are two methods of it. One is the frequentist method, that is using the MLE and MAP estimators for estimating the parameters, and another is the Bayesian technique, where for estimating we integrate out the parameters. Okay, we are going to discuss on that. We're going to solve some problems here, and hope you understand and enjoy. Okay, um, so our first problem is on MLE. Okay, and to explain that, what I'm going to do is I'm going to start with Bishop here. Okay, like a classic book for machine learning. I'm going to explain from here. Okay. Hmm. So as you can see, I think much is not explained here. Maybe your notes is better here. This one, just wait a minute. So where is your so as you can see, so for the maximum likelihood estimation, we need to understand what is likelihood. Uh, so is everything audible?
Yes, it's audible.
Acha, my volume is little low. So let me explain. Okay. Hmm. So what is going on? Yes. So yes. This is the one. Not this one. Okay. Yes. So the likelihood is defined as the probability distribution in which we are looking, which is actually function of theta. Okay. No, theta is fixed. This should not be fixed overall. Uh, okay. And so it is the data given the parameters probability. Okay, and okay, so you have to maximize that, and free illustration here, maybe. Let's see. So so just they have given an example with normal distribution, and as you can see, what we do is given the likelihood, uh, which is in this case this one, because the samples are independently drawn. Okay, so that is why we have made the product of the probability of each of the samples. Okay, is that clear? You understand this part, why the product is coming? Hello, anybody want to say something? Okay, and we take logarithm over that so that the differentiation is easier. So okay, and in this case, suppose there are theta vectors of parameters. So in scalar terms, there is theta 1 to theta p. So we differentiate with respect to that theta, okay, or each of the theta 1 to theta p individually, and we get the values of the parameters that we need. So this is called the MLE estimate. Okay, and something more to explain here. Okay, so as you can see, means like to write the MLE, what we are doing is that for independence condition, this product is coming, and other is the occurrence of the sample given that parameter. Okay, parameter is the value that we need to find, so it is variable, so it is a function of theta actually. Okay, and the probability to understand, right, that samples given theta. Okay, so so that is it. Okay, uh, and so that is the likelihood, and for maximizing that, you need to differentiate with respect to all the parameters, and so you get the examples. So they have given some examples as well in the case of normal distribution. So it's little harder actually, because they have already taken the multivariate one, which is harder to understand. Uh, but like as you can see, so you understand the multivariate Gaussian form? Anybody? No answers? Okay. Anybody want to say something? It's like any problem, in specific problem did you occur in this assignment, or hello? Little bit more interactive would be fine.
Sir, when you will solve the problems, that would be more clearer.
Uh, that is true, but like for the solving the problem, you need some background, right? It's like some problems actually very easy. Okay. But let's see. Uh, so as such, any problem is like which type of questions you could not handle. We can focus more on that. Actually, that is why I'm asking. Hello. Any any suggestions? Okay, you got any
Sir,
suggestion? Yes.
sir, right now it's fine. Up to that point, it's fine.
Acha. That means like any special top means any topic that you specifically struggle to solve the problems. Nothing
If
else.
you can explain that cuff question, the first one,
Cuff. What
cuff and
cuff?
yeah,
Cuff. As you're saying.
yeah, yeah.
Repeat. Cuff. Cuff is what?
The first question of assignment number first question of assignment number 2.
Assignment. Acha. Let's see. So what you're saying is, if we go there, I have so many tabs open. It's confusing. Uh, which is the one? I think this is the one. No. I need to start another. I think. Um, Wait a minute. So this is the old one actually. So if we go to the new one here, Acha, so assignment means like coding exercise something. Hello.
Week 2 assignment, sir. I'm asking about week 2 assignment.
Which one?
That second question.
Actually, you have trouble in this one. It is actually base theory, nothing difficult.
Yeah.
But I will explain. Actually, it is sometimes what happens that base theory is quite confusing
Yeah,
for
yeah.
students. But maybe you can focus on this one as well. Like MLE is quite important to understand as well. Okay. So where was I going? Yes. So what they have done is picked up a multivariate Gaussian. Okay. But the estimation can be easier with a one-dimensional one. So let me show you quickly. Uh, so okay, so likelihood of a multivariate Gaussian is defined as this. So the single variable is oh shit, just draw. So it is 1 by under root 2 pi sigma e to the power minus 1 by half sigma square or something like that. Forgot it. Let's see. It's a half x minus. So we define this as the likelihood here. Okay. And so what does it mean is that given x values, x or y values, okay, only x values here, okay, and given theta is the mu and sigma, okay, occurrence of those given these parameters, okay, so something like this, okay, and okay, and so this is it, okay. So it is, we actually go similar to in the multivariate case. First we take logarithm. uh, so as you can see, first we take logarithm and then differentiate with respect to every parameter, okay, and we'll get actually very similar results, okay. So first we're taking logarithm, so that becomes minus log under root 2 pi sigma, okay, and minus x minus mu by sigma square. We took logarithm first, okay. So as you can see, what they have done is like then differentiated with respect to every parameter, okay. So we are in this case it's mu and sigma, okay. So if you differentiate with respect to mu, this one is already 0, okay, and just summation will be there, otherwise it's not possible, okay, over all the data samples, okay. Okay. So what happens is that x differentiating, what you get, x minus mu by sigma, differentiating, actually 1 by sigma is also there, right? Okay. Okay, and summation over that is equals to 0, okay. So if you separate it out, what happens is that summation over x minus n mu, so it is quite obvious answer, as you can see, it is the the MLE estimate, we're estimating the mean, it is the equals to the formula of the sample mean, okay, which it should be actually. That is how we get the formula of the sample mean, okay. from this MLE estimate. Okay, otherwise it was not known. Okay, we similarly differentiate with respect to sigma and get the formula for the sigma as well. Okay, so little exercise before getting to the question. Okay, so anybody has done this question? Hello, anybody has done this one? uh, this question, as you can see, MLE we have to find out. Participation is quite low today. Anybody can answer? Yes, Ravinder.
Sir, it's B,
It's B.
I guess.
Acha. Well, let's see. So we actually proceed similarly. As you see, the form of the Bernoulli distribution is like this. Okay. So what does that mean is that uh, is the PMF. Okay, called PMF. Okay. So so this is the distribution. What does that mean is that uh, you are finding the probability of occurrence of a sample, suppose x1. So that would be p up p. So to make you clear, actually, uh, what happens is that in this case, these samples are like coin toss. You understand Bernoulli distribution? So in Bernoulli distribution, what we get is 1 0 1 0 like that. So x1 to xk are like 1 0 0 1 type. Okay, and the probability is defined by this. Okay, so actually what does this mean, you have to understand, is like, suppose we have to find the probability of occurrence of 1. Okay, so what we're going to do, we're going to put x equals to 1, so answer we get is p. Suppose we need to find the probability of occurrence of the experiment of the sample in which we get x is equals to 0. So the probability we get is 1 minus p. Okay, so you can understand, we put 0 here, this one becomes 1 and this one becomes p to the power 0, that is 1. Okay, so the answer is 1 minus p. Okay, any doubt up to this point? No doubts, right? Simple enough. So actually it is defined in such a way as only like whenever you get put 1 you get p, whenever you put 0 you get 1 minus p, and the definition is like that. So as you can understand, first what we are doing is that to estimate the parameter we have here is p. Okay, what is the, you can say, the mean occurrence probability of uh, of a event here. Okay, uh, so let's continue. Okay, so p we have to estimate. Okay, occurrence of, that is occurrence of, means the p is the expectation in this case. Okay, if you understand. So what we are trying to find is the occurrence of 1 or the expectation here with MLE. That is the only parameter we have here. Okay, so so we're trying to find the expectation here. um, Now next what we do is yes, so as you can understand, the samples are here independently drawn. Okay, so the likelihood is defined as, sorry, so the likelihood is defined at as a product over all the probability of each sample. Okay, so what is going to become is p to the power xi and 1 minus p to the power 1 minus xi. Okay, so how do we get into this actually? Just so from probability theory we know that suppose we have n events, okay, and we want to find the occurrence of all of them at once. Okay, so that is equals to uh, so this is this so this is the probability of occurrence of all the events at once. Okay, and okay, so they all occur together. Okay, so if the events are independent, what happens is uh, okay, you can write is it like this, right? Everybody knows this one. Okay, if the events are independent, you can write the probability of occurrence of all events as the product of probability of all events. Okay, and from this you can understand like mm, well, nothing much to understand. So this is it really. So in the likelihood case, we're also trying to find the probability of occurrence of all the events. Okay, a combined measure. Okay, for that. So okay. Uh, so next, what we're going to do is insert another slide. So MLE in our case represented by L, suppose. So that is going to be sum over I P xi 1 minus P 1 minus xi. Okay. The next what we're going to do is differentiate L with the only parameter we have, that is P, probability of occurrence of 1. Okay. Okay, so we did that. Acha, for that we need to take logarithm over that, otherwise it is difficult to differentiate this expression. Okay, so what we're going to do is summation over I xi log p plus summation over I 1 minus xi 1 minus xi log of 1 minus p. Okay, so we take differentiation with respect to p, so what we get is xi by p, and we are differentiating with respect to p, so this becomes 1 minus p, another minus comes here from chain rule. Okay, summation over this is equals to 0. Okay, so what do you do next is as you can understand, this is p is independent of the summation, so you take p out, this is what you get, and next what you get here is 1 minus p is independent, so that is also comes out, and summation over this is n minus summation over xi equals to 0. Nice. So next what we do is, so we'll take LCM here. Okay, and what you get is 1 minus p summation of xi minus p summation of n minus summation of xi. Did I get anything wrong? good. Let's see what happens now. So, did anything wrong here? Should I did anything wrong? So it works out. 1 minus p minus should come out. Okay, looks good. And hmm. Let's see. 1 minus. Okay, so let's p take p terms common. So this becomes minus xi. Are you getting plus here? That is disaster. Acha, p terms, right? What did it say? P terms. Acha, acha, that is okay actually. Minus n. Okay, so this cuts out. Okay, and the next what we have is summation of this will become minus xi. Other side, I take it other side, and uh, is it audible properly? Audible, everyone?
Yes, it's audible, sir.
Yes. Okay, let's continue. Uh, so you can understand this one, no problem, I think. And so this is done, I think. Okay, so this is the one. So this minus is going to get cut. Okay, the answer we get is the estimation of the probability of occurrence of 1 is, okay, got the answer. So what is this? Mean of the samples. Okay, so the answer is mean of the samples. Okay, so where is our presentation? Oh my god, too much. So this is the mean of xi. Got it? Any doubt? Anybody? Any doubt?
No, it's clear, sir.
Clear. So your answer was wrong. So what did you do wrong in this case? Hello. What did you do wrong in this one?
Maybe I have not considered that mean the
Summation over one, I think.
yeah.
Acha. Okay. Another similar question actually. But in this case, what you have is a prior. Okay. So what you do is that. So they have called for a MAP estimate. So that is the maximize the posterior. Okay. So posterior is defined as the prior times likelihood by evidence. Okay. But what happens is that what happens is as what happens is that the evidence part, okay, is not dependent on the parameters because we sum the parameters out. Okay. uh, so evidence, actually I should explain it more, I think. So you may not be familiar with the words evidence and everything. So this is the MAP one. Let's see. Okay, so this is the one. Okay, so this is called the uh, not going able to use. Let's download. Okay, so let's see. So this is called. So not able to use. Okay. Okay. Uh, so so this is called. Still not. Oh my god. It may not be text actually. That is where the problem. So how can I do it then? Maybe some drawing tool. Yes, I got it. So this is called the let's just underline. So this is called the prior. Okay. This is called the likelihood. As you could see, the occurrence of x given the parameters. Okay. Here the parameters are the actually variable. Okay. But okay, the distribution is of the parameters. Okay. And we are finding this distribution. Okay. In which we are calculating the probability of occurrence of the x values with respect to okay the parameters. Okay, so this is called the what do you call this posterior. Okay, probability of occurrence of the parameters with respect to the x values and theta. Got it. Okay, and this is called the evidence. And interesting thing is you will see is that we are adding all the w means the all this conditional probability with respect to wi. Okay, what happens with that is that you remove the wi parameter altogether. Okay, so this is not actually dependent on wi. So while maximizing the posterior, we only take the prior times likelihood. We do not take the denominator because it is a constant for differentiation. Okay, it is a what do you call that, a normalization value. Okay, normalization constant. Okay, it is not a it is not dependent on the parameters. Okay, parameters of differentiation. Okay, clear everybody. Why in MFE we do not use the full MFE, just prior times likelihood. Hello, everyone got it?
Yes.
Yeah.
Yes, sir.
Yes. Thanks. So is it fast? Are you able to understand or
Yeah,
is it
little bit. It's typical.
difficult, right?
Yes, yes.
So like Devinder, you can keep your mic open. Okay, you can ask me which part you are facing problem. Okay, so they can I can understand more which area to focus actually. Which part you are not understanding? MLE was clear. MLE is not easy as well, right? Uh,
Yes, yes, that is clear.
MLE is clear. Acha.
Yes.
So this is the one, right? MLE, as you understood, like just going through it again. So first, the probability estimation for each sample. Okay, probability of occurrence for each sample. Okay, and we product over these because we are trying to find the joint probability. This is called joint probability or occurrence of all the samples. Okay, at a time. So that is called the likelihood. Okay, occurrence of x values means all the x values. Okay, so after that what you did was to take logarithm for easy differentiation, and then we just did it. Okay, to estimate the parameter p. Okay, p is the occurrence of samples which are 1. Okay, it is also called the expectation in this case. Okay, or mean also same. Okay, um, another exercise I can show you is like this is the PMF, right? To find the expectation, what you have to do is that what is it? Yes, Borugula. Yes, read out, read out. Ramamurthy, read out. You've raised your hand. Okay. Okay, let's continue. So we what we do is we have to find the expectation. Okay, and for expectation, what is the thing we can do here? Yes, yes, you can speak up if you want. No, you can unmute actually. No problem. So okay, so I got distracted. So we need to find the expectation, right? Yes. So for expectation, what we do is so this is the PMF we have. Okay, okay, and for expectation. One minute. Acha, acha. So expectation of a random variable. Acha, expectation is not the same here actually. We find the expectation with respect to x. Acha. Acha. We'll I think catch up on that later. Uh, so actually focusing on MAP. MAP you have doubt, right? So Devinder, what you're saying? MAP is difficult.
Yes, a little bit. It's
Acha.
typical.
So let's focus on the expression again. Uh, what was that? Okay. Maybe not this one. Okay. Acha, we have downloaded that one. Okay. So as you can see, you understand this expression is the Bayes theorem. Okay. Devinder, you're on me. This is Bayes theorem. You understand this?
Yes, yes, yes.
And this is called posterior. You know that.
Yes, sir.
So this is called the prior. Okay. And what
Yes.
does prior represent is that what prior knowledge we have about the distribution. Okay. So prior is used for various purposes. Okay. It introduces how means like the distribution is going to be closed. Okay, means like towards the how how close it is to be the mean value. Okay, so let me just give an example. So what happens is that this is our suppose Gaussian distribution. This is our mean. Okay, and so these are close, quite close. Okay, others are not. Okay, so what majorly we use the uh, this what do you call this prior for is to like make it steeper and this line thinner. Okay, so less density away from the mean. Okay, and so for that we use Laplacian prior. Okay, and that is very popular for this. Okay, robust estimation for that, but like overall that is not needed. So means like what you can understand is like we can give different shapes to the our distribution. Given suppose we know that already know that data mostly lies near the mean. Okay, so like that we can choose the prior. Okay, so like this is a more flatter one. Okay, more so this is thicker as well. Okay, if supposed to have the same number of data points, and so like this is the significance of prior in this case. Okay, likelihood is okay, so prior complements the likelihood to create our original distribution of the data. Okay, that is the posterior. And as you can understood, I explained that as we sum over the wi. Okay, so actually this is from the total probability thing. Okay, suppose we have pc we need to find. Okay, and so this is defined as supports suppose you're doubt actually in this question. Let's take that one to make it very clear actually, and it will clear that question as well. So let's take this question actually. So as you can see, we have occurrence of C, okay, and it is like over these two space, like where F is occurring, where F is not occurring, okay. So over that we have C here. This is the inner circle, okay, occurrence of C. So the probability of C, this is the total probability of C, can be defined as the probability of F, okay. So F has occurred, give, and then this has occurred, okay. Next what happens, probability of F not occurred, and probability of C given F not occurred, okay. Very simple, right? As you can see, if F has occurred, then C can occur. If F has not occurred, then C can also occur. Acha, yes, so adding two cases gives the full circle, that is the probability of C, okay. and so this is the theory of the total probability, okay. How do you derive this? Not difficult again, okay. So PC, okay, is given as P of F intersection C, okay, and this is defined as P. So as you can see, sum of the two areas, and this is F intersection C. From set theory you understand that, and this is F bar and intersection C, okay. And from what do you call this, what was called this, conditional probability theory, not theory, I guess it's conditional probability. How do you write that? Suppose C given F, okay, this can be written as P of C intersection F given F, P of F, okay. You know this one, right? Very, very simple, okay. So you just put this intersection one, okay. So you actually get this expression. So it's called law of total probability, okay. And so actually very simple question actually, but sometimes get confused in Bayes theorem as well. Let's solve this one. What happens is that you can understand the MFE part better with this question. So I hope it is not too fast. Is it fast? Hello? Hello?
No,
Not fast, right? Thanks, Millie. So maybe Millie and Devinder both can unmute themselves and guide me through the lecture, okay? And any problem you are having, unmute yourself, please. Hello?
yes, sir. I will
Okay.
take.
Devinder, maybe not here. Acha. Keep yourself unmuted, okay? Okay. Yes. Millie as well, I think. Okay, let's continue. So, Devinder, it wasn't too hard, right? Fast.
Yeah, yeah,
Understood?
it's
Total probability, got it?
hmm.
So next, let's understand the problem here. So, so you're given this situation, okay, and you need to find this one. So this is actually a Bayesian network, okay. So the I don't know how much it is covered in the lectures, but it represents a directed acyclic graph. It is just a line in this case, okay, simple enough. And the line, the arrow from which it comes is actually independent, and the arrow to which it goes, okay, is dependent on the variable that the arrow comes from, okay. Maybe a little complicated, but what I mean to say is that f is dependent on dependent, how would I write, on C, okay. So this is Bayesian network. Much more theorems are there, but I think we should not go depth on that. Okay, um, as it is not very important. Just a representational one. though you can solve complicated problems in a simpler way through this. That benefit is there, but I don't think going into details in this course is a good idea. Um, so 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 with this, what I gain is that I need to find p of f given c, okay, because f is dependent on c, okay. That is what I gain. That is what they have told me to get as well, okay. So what is this? P of f intersection c divided by p of c, simple enough, right? And now you have to understand, in the other case the c is dependent on f, okay. So these are two separate cases, okay, but they have given that the joint probability remains the same, okay. So c so this is a
हाँ
joint
जी
okay, so this is a
कोर्स है
joint
यार एक वो पढ़ रहा हूँ
so this is a joint probability, okay. You understand what is joint probability? Just occurrence of both the event, okay, joint occurrence, okay. So we need to find this one, right? So that remains the same, so we can get this from this one, okay. So okay, so okay, maybe not that easy as well a question, because you have to understand a lot, okay, in this question. If you understand that, it is easy, okay. So next what we do is that we need this one, right? Okay, uh, let's see. So we need to find the intersection, right? Okay, so not very hard actually still. uh, so just we'll use this one, okay. P of c given f, okay. In the previous diagram, as you can see, this one, P of c given f is given, that is equals to intersection 1, that is what we need, okay, divided by P of f, okay, that is 0.1, okay. Now the result is equal to 0.8, okay. So we have got P of f intersection c equals to, this is 0.8, so this becomes 0.08. So we got the intersection, as they say the joint probabilities remain same, okay. And so that's one thing. And next we need to find the P of c, okay. And so this is also very interesting one. Also yes, yeah, maybe not that easy question. So as they have said, the joint probabilities remains the same. So this is a joint probability, okay. This is also a joint probability, okay. So they remains the same, so PC also remains the same, okay. Okay, and from this formula we can get the value of PC, okay. What is this going to be? PF 0.1 multiplied PC given F 0.8, 0.08, acha, no, 0.8 actually. So this is 0.8 plus what we're going to have is P F dash, that is 0.9, simple enough, right? 1 minus, okay, and P C given, not F, okay, that's 0.3 given, okay. How much this becomes? 0.08, 0.9, 0.35, right? Yes. So we get PC equals to 0.35 from here, and to get our answer, what we're going to do is just divide. So this is our answer by okay, divided by 35. Okay, understood? Understood? Any problem? Millie, Devinder.
Sir, could you please explain
Hello, बोलिए. Could I
एक
explain
बार
again?
आप हाँ या थोड़ा एक बार दोबारा बता देंगे तो.
अच्छा, this one. Okay.
Yes.
Okay, so let's go over again. Okay. So I explained the law of total probability, right? This is the one.
Hmm.
Understood this one? How can I compute PC given the conditional probability? Devinder?
Yes.
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 Okay. So that one we can start. So from that I calculate the PC value as well. Okay. This is the one.
PC is PF into PC by F.
PC is equal to PF into PC by F plus P of not F multiplied P of C by not F. Okay.
Okay.
Simple,
So it
right?
comes,
Understood, right?
yes. So it
Hmm.
comes 0.1 into 0.8
Hmm. So
plus
total
0.
it comes 0.35.
Okay, okay, okay. The values which are given, you have just simply put those values.
This one is also there. The 0.9 is the 1 minus 0.1. Okay.
Yes.
This one you can understand.
Yes, yes, yes.
So the next we've got is that P of F given C. That is what you need to find is the joint probability of P of F intersection C and P of C. Okay. P of C
Yes.
we have got intersection C is 0.1 to 0.8. Okay. This is the ratio of that is the answer. Okay. Got it.
Okay.
Okay. So actually next we're going to focus on MFE and okay. What is that? Yes. So as you can see, so this is equivalent to probability of C type. Okay. Probability of C. You understand? Okay. So in the example that we took, actually in that question, what we found out was that there's a PC probability. Okay. So what is this called? The joint total probability of occurrence of C. Ram, if you can unmute yourself, actually, no problem. But he is not doing it. So what was I explaining is that hmm, hmm. So PC is the total probability. Is I was explaining is that when we are summing over every value of x, okay. So when we are summing over every value of f, okay. So f takes value 1 or 0, okay. Occurrence of f or not occurrence of f. It can be many other values as well. Means like in another situation. So if we sum over these, okay, sum over the values of f, what we get is that the final result is not dependent on f, right? Got it? Devinder got it? Millie got it?
Yes, sir.
So so the final value, that is the PC, is not dependent on f if we sum over f. Okay. So that is what I'm saying here as well, that this denominator is the sum over all wi. Okay. So what happens is that it is not dependent on wi. Okay. So that is a constant for the differentiation that we are about to do. Okay. for maximizing the posterior, that is MAP, we do not take the full MAP. We only take the prior times likelihood. Okay, prior times likelihood. Times means multiply. Okay, so that is what only took. We do not take the evidence. Is called the evidence. Okay, this base is called the, this denominator is called the evidence. Okay.
हेलो.
हेलो. हाय.
हेलो मैम, बताइए.
क्या हाल चाल?
बस जी ठीक है, आप सुनाओ.
मेरा भी ठीक है.
Okay. So that is what I am explaining, and so you can understand that one. So MAP is the prior times likelihood. We do not take the evidence at the denominator. It is irrelevant. Okay, it is a constant. Okay. So as they have given the prior. Okay, and but the likelihood is where do you get from the like? So likelihood is this one. Okay, x given theta is the condition for likelihood. Okay, so this is the likelihood. Okay, x given theta, whenever you find it is the likelihood. Okay, and so we multiply with that. This is prior times likelihood. And mod x is also there, right? I think, or what? uh, mm, so what do you got answer in this question? Hello. Hello everyone. So what answer you got in this question? Anybody? Anybody? You haven't solved it? MLE, you have solved it?
No,
Davinder?
sir.
No. Acha. And is there the model? I mean, say, is there any answer given? Actually, I'm doubtful about the mod x part. Is it part of the inequality or of the part of the likelihood? Any answer sheets given? What can be the answer on this one? Okay, let's continue. Okay. Uh, so don't think the mod x is part of the expression for likelihood. It is just mod x greater than 0 is also useless thing. I think it is part of the. So let's try. So next what we try to do is, like, we have to find the theta. Okay, estimate theta, e to the power minus lambda theta plus minus theta x. Okay, and actually mod x is quite irrelevant in this case because we're differentiating with respect to theta, right? So mod x and lambda are constant, so they're going, it is as good as not writing down. Okay, next we'll go to 2 is differentiate with respect to theta. So this is e to the power, this comes, so just write it as t. Okay, and next what we do is that uh, so leave theta alone and differentiate with respect to this, differentiate this. Okay, so this is t only, and this differentiation will come as minus lambda plus lambda minus, I think. lambda minus x. This is equals to 0. So you cut down t, and then what you get is that theta equals to 1 by lambda plus x. Okay, so any doubt? We got the answer, theta value from MAP. Any doubt? Millie, Davinder, Sanjeet,
No, sir.
Samruti. Okay, no doubt, right? Easy. Let's see, anybody else is there? Not going to reply, maybe, or whatever. Let's see, continue. So this is what we have done. Okay. So disadvantage of KNN classifier as a classifier is very simple as well. To recall KNN, what we do here is that we already have a classified points. Suppose head and tail. Okay, this crosses a head, and this is tail, something like that. So suppose I take a new point here and represented by a square. Okay, so what we're going to do is suppose we take so k means like we take k is a parameter here actually, and we take the suppose 3 nearest, then k is 3. Okay, so we take distance from 3 points. Okay, so as you can see, distance from these 3 points is the minimum. So we this tail, we tell this sample is a tail, not head. Okay, next thing what we is the problem is that suppose like, so this is there, these points are there. Okay, these points are there, and there is a big cross here, and there is our turning point. Okay, suppose we take two means like k equals to 2, then what I take distance from this tail and distance from this head. Okay, so the means the classifier is inconclusive. Okay, if there is more outliers, suppose cross, and I'm taking suppose 2 or 3, then what can happen is that the classifier may not work because of the presence of the outliers. So KNN is quite sensitive to outliers. This is the best one actually option, but it is also in large data set it is not very effective. That part is also remains, but I think the most important point is this one. Okay, clear everybody?
Sir, in the
Hmm.
previous question,
Which one? This one? MAP?
no, 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 no. It was next regarding the K.
It's okay. Okay.
No, no, not that. Ah, yes, here, sir. There are two. First one is fails while handling the large data set. That also can be answered.
Yes, you're correct in that. But I think the outlier part is also very important. Means like, is the answer given already? Uh, which answer is given?
So no, I think it is large data set. Also, it is also failing.
You're correct. You're correct. So both can be answered
O-
actually, A and
Okay,
C.
okay.
But like we have to choose a more important one. I thought this is a
Third
more
one.
important one. Okay.
Thank
Data
you, sir.
set.
Thank you.
Yes.
Thank you. Thank you. Thank you. Thank.
Thank you very much. Yes. So what I understood was like the data set. If you have a better computer, you can handle a bit large data set. But if the outlier problem is that it cannot be handled with more resources. Okay. So that is how I decided like this should be the answer. Okay. This thought process actually. Uh, so another question with such. dual answer maybe, I think. Just let me take a break, okay? We will catch up after 5 minutes, okay? Okay. So we'll meet at 7:11, 15:11. I mean, what means 5:11, okay? So, welcome back, everyone. So, to continue, um, some numbers have reduced in the break itself. Mm, that's okay. Okay. So, let's continue. Um, so, the first is that odd values we do prefer because means like in even values, what can happen? The tie can happen. Okay. There is undesirable situation when you are voting. Okay. So do prefer odd values. Okay. And the second part is also right. Okay, because what happens is that in k nearest neighbors there is no training time. Okay, we the test time is the training time itself. Okay, we are not testing separately. Okay, with the sample itself. Okay, with the test point we train and test at the same times. Okay, it's like it's not very hard, like let me explain. I'll not leave you abstract here. So when we are taking this square, okay, so we are calculating the distance. Okay, so if for another point we are also taking a point here and we are calculating the distance. Okay, so for each test point we have to calculate the distances. Okay, and take the three minimum. Okay, suppose k equals to 3. Okay, so for each time we have to do this process. The training happens again and again with testing. So what happens is that there is no training process. Okay, but the testing is there and we do it again and again. So more computation is surely on test time. Okay, so this is also correct. Okay, uh, so these two are correct. Okay, and you say which is more important, then I think this one is more important. Okay, so should be the answer. It does not work well with high dimensional data. Okay, uh, the distance part actually is difficult in higher dimensions. And the next is the optimal value of k is highly dependent on the data. That's not correct, it's very dependent on the data, because how many neighbors you take is a problem specific situation. So there is no hard and fast rule here. Okay, and this is another MLE problem. So any problem with this one, I think you can do it yourself. Anybody? Millie, are you there? Millie? Yes, Millie. So question number 6 is doable after all the MLE we have done. Millie? No?
Yes, sir.
Yes, so just tell me, 6 is doable? Doable? You can do this
Yes,
one?
sir. Yes, sir. I will try and
Yes.
ask you later on if having any problem.
Uh, so you already would have some thought process after MLE, after all the MLE problem and discussion we have done. So uh, what do you suggest? How do I start actually here?
Suppose x is a still know the following over the mass function.
Yes, no pressure, no pressure. Okay, do it easy. Okay. So first you should remember that for MLE we need to first write the likelihood. Okay, so likelihood in this case what that will be is the product of occurrence of all the events. Okay, okay, Millie, got it? Hello, where are you?
Yes, sir. Yes, sir.
Yes, so how do you write the product of all the probabilities here? Help me with that one. You tell me, I will write it down. Okay, you understood the point that for like to write the likelihood we need the product of all the probabilities of all the events. Is that correct?
Yes, sir.
Yes, so how do you write the probabilities? How will I write the likelihood L? How can I write that?
Mhm.
Okay, no pressure, no pressure.
into 0. Mhm. So in the second data, in the where x is equals to 2,
Hmm.
I am having problem in 2 into 120. We are going to write this?
120. Acha, no, no.
Divide by 3.
Actually, the thing is that the zero you're thinking is actually theta. Actually, so this is so for
Okay.
2 it is 2 1 minus theta, not 0. Okay,
Okay. Okay.
but it
Okay.
is so weak actually.
Mm-hmm.
For 0 it is 2 theta by 3. For 1 it is theta by 3, and for 3 it is 1 minus theta by 3. Okay,
3.
got it.
Okay, sir.
So this theta by 3. Okay, so how do I write the likelihood here?
So we have to write in the intersection form the probability of
Hmm.
all the.
But you also remember that in this case we already consider that the probabilities are independent of each other, right?
Yes, sir.
So what happens in that case if probabilities are independent?
Sir, I don't remember that exactly a probability
No problem.
section.
That is why I am here. Okay. So if this is what I need, right? For likelihood.
Okay, sir.
Correct, right? So if
Okay,
these are
sir.
independent, what we get is that
Mm-hmm.
multiply the individual probability of all the
Probability.
events, all the samples. Okay,
Okay, sir.
right? So this is one.
Theta upon.
Okay, like that. So product of these. Okay. So how do I write the MLE?
Hmm.
Means the likelihood then?
Sir, we'll directly write 2 theta upon 3 into theta by 3 into 2 into 1 minus theta by 3. Directly
Yes.
we are going to multiply this.
Yes. Very nice. Very nice. That is the idea. But if you can understand that zero, we have two occurrence. Okay. So I can write this as square, right?
Mhm.
Okay. To shorten our hard work. Okay, this will be
Okay, sir.
multiplied later. Okay, so I'm just taking those together and writing as square. Okay, so for
Mhm.
one will what we'll get is that theta by 3. See that one is 3 times, right? This is going to
Yes.
become cube. Then
Okay.
what is going to be 2, right? So you tell me. 2.
1, 2, 3 times. There is 3 theta by 3.
Yes, 2 times.
3. It's 3 here, sir.
Acha, power is 3, right?
3.
Power is 3. It is correct.
Okay, sir.
And next 3, how many 3's are there?
2.
2, right? So what will be the expression here for 3?
For 3, it is 3. 1 minus 3 into 1 minus theta upon 3 to the power 3.
3 into is not there actually, so this is going to be
Oh,
power 3. Or
3
2
only.
is there actually, 2 3s are there.
Oh, sorry, 2. Yes.
Okay, so this is the likelihood. So you have to maximize. Before that you need to take logarithm of this. Okay, and from here you can do it, right? Nothing difficult.
Okay, sir.
Okay,
Okay, sir.
so anybody has any problem? Any problem?
No, sir. No, sir.
No problem, right? You can do it.
Yes, sir.
Okay, so let's move on and get to this question. So this is a very simple problem as well. When the k is 1, we are taking what we are having is a bias. Okay, bias for one
Understood.
nearest neighbor, right? How can we be so sure that it can be one nearest neighbor is enough? Okay, it's like more. the doubtful person will take more number of neighbors to estimate the class. Okay.
Okay.
So what happens is that when we have a bias, the 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 what happens is that when our model is biased, what happens is we are underfitting. Okay.
Perfect.
Okay.
Hmm.
So that is from the bias variance trade-off theory. Okay. So
Okay,
where
sir.
underfitting is the answer. Okay.
Okay, sir.
Next we move on. A difficult problem actually means difficult lot of calculation here. So this point is given, which class it belongs to. What you have to do is you have to take the distance. Okay. 5 such neighbors, so you have to take distance from all of them. Okay. And the 5 the then take the 5 least distance. Okay. And have a voting there. Okay. Which, suppose there are 3 which tells that there are class 1. Okay. So have a voting there to know which class it belongs to. Okay.
Okay, sir.
Got it, Millie?
Okay, sir.
Hmm. Okay. Clear enough, right?
Okay, sir.
What you have to do is take the distance. Okay. Distance is that difference square plus difference square under root. Okay. And
Oh,
take the least 5. Okay. And see which
mhm.
class they belong to. Okay. And
Okay.
that majority is the answer.
Okay,
I
sir.
haven't done this because it would work so hard. Uh, then the next question is that Parzen window method. You know what is Parzen window? Should
No,
know.
sir. No, sir. No, sir. No, sir. No, sir. No,
No.
sir.
Okay. So let me explain. This is so as you can see, so this is the probability density px. Okay, rho x I think, and so that is called the probability density function PDF. Okay. So we're integrating over that. What we get is the probability or the CDF. Okay.
Okay, sir.
So that is called the CDF. Okay.
Mm-hmm.
And so it is something like this. We are integrating over region R of dimension t. Suppose the dimension is 3. Okay.
Oh,
So if the density is not dependent on the dimension, we can take the density out of the integration. So what we get is
okay.
volume. Okay.
Okay, sir.
So and from this they have from MLE I think, they have
Hmm.
estimated P is equals to K by N. Okay. So we
Okay.
put the value K by N, and K is the number of points that fall in the region out of out of total N points. So that is the density here. Okay, got it.
Okay, sir.
There are some parameters, the conditions that need to be satisfied. Nothing serious here. And so Parson window we need to find. Okay. So the VN volume is fixed. Okay. Okay.
Mm.
And some KNN thing. Okay. And so as you see, so this HN. So we have taken a cube. You can say cube or a d-dimensional whatever cube. And so what we do is that Vn is there, Hn is the side of the cube. Okay. And we define the window function as the function of u such that it becomes 1 if uj is half less than half. Okay.
Okay,
And
sir.
otherwise 0. So what is u here actually? So u, as you can see, well, we cannot see, let's see, u is not written. So u is this ratio. Okay. X minus x bar. So this x bar is what y bar represents is a vector. Okay. So this is the point of consideration x underline I is the all the rest point. Okay.
Okay,
So
sir.
if this ratio is less than half, okay, less than equals to half, then
Okay, sir.
it will be 1, otherwise 0. Okay, so that is how we get the kn value. Okay.
Mm-hmm. Okay, sir.
So this is the most important part actually here. This condition less than equals to half. Okay, some integration here and there and proof. Okay, nothing
Okay.
to understand here. So what we next do is like so this density is equals to 1 by n of this summation of this. Okay. Okay. So this
Okay,
is
sir.
called the from the what you call this KARZEN window we calculate the probability density function. Okay, like this.
Oh,
So let's move on. Uh, so the size of the bandwidth parameter. Okay, that is this one. This one. Okay, bandwidth parameter. I think this is the one. I'm not wrong. So this is the size of the neighborhood, like for KNN, size of the neighborhood around a test instance. So how much size do you want? Okay.
okay,
So
sir.
that is the definition actually. So nothing can be done
Okay.
about this. And so and so we are looking for the query point. Okay, and this is the width given. Okay. Okay. So what is it like? It is actually on a line. Okay. 0.5, and this is the word width 0.3. Okay, length. This is half of 0.3 is 0.65, and subtracting half of 0.3 is
One.
0.45.
Oh,
Very nice.
0.
Okay, so this is the width under which the point, if it is inside, then we will use the value as 1, otherwise 0. So if 0.5 is within, but 0.57 is outside.
Outside the value.
Okay, so 1
Yes.
by 2 number of points is this. Okay, then below we also need the uh, width. Width is also needed. Okay, because like volume q was there, but it is only a line, so this is it. Okay,
Okay, sir.
and next what we have here is summation over both the points is there, but one point is equals to 0. Okay, another is
Oh,
a 1. Okay,
1.
for one point, and for another point it is 1. Okay,
Okay, sir.
did you miss something else? No. So 1 by 0.6 is the answer. So I think this is the one. Okay, done.
Okay,
Easy.
sir. Yes, sir.
Next, repeat the question. I think I'm not able to get it. So number of data samples become very large, then what happens is a Bayesian estimation in which we integrate out the parameters is is a uh, is a what do you call that, intensive process, computational expensive process. So
Yes.
what happens is that is becomes worse than MLE. MLE is better in that case. Okay,
Okay, sir.
so this problem we have already solved. And other than that, what we have here is that Bayes' decision theory assumes that they are identically distributed. Okay, no, not identically. Uh, feature vectors are identically distributed. Yes, identically distributed. Okay, so feature vectors means the features that we have are of the same distribution. Okay,
Okay, sir.
next is also very simple, minimizes the loss function. This is a directed acyclic one Bayesian network. So we can now focus on this problem. Okay. 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 So let's continue. So in this question, what we have here is that So this is the this is the predicted ones. This is the truth value. So spam, not spam, spam, not spam.
Yes.
Okay.
Yes, sir.
Assume that the word offer occurs in 80% of the spam messages in my account. Okay. So in 80% of the spam messages there is offer. Acha. Also assume the offer occurs in 10% of the desired emails. Okay, so they are not spam. Okay. If 30% of the received emails are considered as spam, I will receive the new message which contains offer. What is the probability that it is spam? Acha. So 30% he is receiving is a scam. It will be not scam, spam it will be. Okay. Now we start with the tree diagram actually, just I have shown in previous day. So this is me. Okay.
Okay.
So this is me. I know that I draw emails, I see emails, I know that there are 30% spam ones. Okay, 30 by 100. There is 70% not spam. Right.
Yes, sir.
So they have said that 80% of the spam messages have offer word. Okay. So for 80% of the case, this is 0.8 into 0.7. Okay. And which do not have the offer word is 0.2 into 0.7. Simple.
Yes, sir.
And in the desired emails there is, in 10% case there is offer word. Okay, this is the desired one. Actually this is spam one, so so mistake actually, this is the spam. Okay, so here it is 0.3 into 0.8 spam and offer word. Okay, here it is 0.3, 0.2 spam and not offer word. Okay, next what we have is 0.7 and offer word happens in 10%. Okay, 0.7 into 0.9, not spam and not offer. Okay,
Okay.
so what is the probability that it is spam? The spam probability is this one, right? Okay.
Hmm.
uh, acha acha given that 30% are spam. Acha, I receive a new message which contains offer. Acha, we have given that we have a new message which contains offer. Okay, so offer ones are this one, right? This is the offer one situation, and this is the another offer one situation. So what we'll have here is 0.3 into 0.8 plus 0.1 into 0.7, and given it is spam. Okay, so spam one is this one. Okay, so 0.3 into 0.8. So if you divide, what you get is 24 by 24 plus 7, 24 by 31. This is the answer. Okay, any problem? This is Bayes theorem. We solve with tree diagram, which is because you have to think less and you can do it quicker. Okay, but with Bayes theorem as writing the expression, you can do it.
Okay.
Okay, so what will this be? We write the expression. So we write the expression for
774.
probability of occurrence of Offer, okay. Offer we know, okay. And so probability of occurrence of then offer is there, okay. So offer is represented by O, probability of O multiplied probability of spam given offer is the one divided by probability of the probability of spam, okay, the total probability as you know, probability not O, probability of S by not O. Using the Bayes theorem
Yes,
expression,
sir.
that is what we have used, right?
Okay.
Got
Okay.
it?
Yes, sir.
So we finish here, okay. Thank you.
Yes.
Any doubts?
Oh,
Any doubts? No doubts, right?
no, sir.
Thank you very much.